Okay, so how it's
perfect.
It's perfect. Okay, thank you.
Okay, so before we start with the last talk of the morning session, I would just like to make a couple of comments. So about the structure of our schedule, I wanted to point out that we have decided to finish the talks every day at the very latest at 3:30 because there are many participants in another time zone. So that was to accommodate them. There are two short days, and that's the Wednesday and the Friday. There we really finish already at 12:30. Today at 4:30, there will be the reception here in the coffee room at 4:30. The last talk today is at 3:30. So in principle, we have 1 hour before that reception. And we are planning informal dinner in a pub on Thursday. The pub is called Pre-Nap, a very strange name with a very strange menu. There is a prenup and post-divorce and things like that on the menu. So if you want to join, you can write down your name on the sheet that Mikhail Matusinski put in the back of the room. And there it will be, everyone pays for themselves. Is there anything else I'm forgetting? No. Okay, so that's it. And very nice to see people here sitting in front of us. And pass it to you.
Okay, well, so next speaker is Beatriz Molina Samper from the Universidad Autónoma de Madrid. She's going to speak about towards reduction of singularities of generalized analytic functions.
Now, thank you very much for the invitation to give the talk. It's nice to be here again in a conference, seeing people face to face. That's good. So I'm going to talk about the problem of reduction of singularities of generalized analytic functions. This is a joint work with Jesus Palma Marquez here and with Fernando San Sanchez. And well, that's what I'm going to do. This is the scheme of the talk. So first, I'm going to introduce briefly the categories of generalized and the standard analytic manifolds, and later I'm going to pass to talk about the blowing up morphisms in these categories and the local and global statements of reduction of singularities. And so as a first approach to the global statement, we present a stratified version in the third part of the talk, and we devote the last part to give a sketch of the proof of this stratified version. Okay, so well, I want to apologize with people who knows very well the first 2 points, but I think that I need to introduce these definitions. Okay, so in order to give the definitions of, so to introduce these categories, we need first to build to talk about the local model. So we need to talk about standard and generalized analytic functions defined in the first orthant of the space. So a standard, well, we take a function, a continuous function defined in an open set. We take a point that up to permutation of coordinates, we can assume that has the n minus e first coordinates different from 0 and the other one's equal to 0. And the function is a standard analytic if it is the sum of a usual power series, convergent power series. So we can also say that the function extends to a real analytic function in the usual sense in an open set, in an open neighborhood of the whole space, removing the boundary. Okay, if we change the word standard by generalized, we have that the function is generalized if it has also a power series expansion, but the support, instead of having the exponents, how can I use this? The exponents here in the set variable, instead of being natural numbers, they are allowed to be real positive numbers, but with the property that they are contained in a product of well-ordered subsets of the real positive semi-line. So we can say that the function is the sum of the have a convergent generalized mixed power series in the sense of Van den Ries and Speiseger. Okay, so with these definitions, we talk about the sheaf of germs of standard or generalized analytic functions in the ORTAN. And when we put it together with the topological space, we have a ringed space. Yeah? This ringed space is a local ringed space because, as we have already said, the germs are locally isomorphic in one case to the convergent usual power series, and in the other case to the generalized mixed power series. Okay, and well, just that we have an inclusion of sheaves that standard functions are generalized functions and general functions are continuous functions. Okay. So with these local models, we build we define what are the A manifolds. We write A in order to talk about both the standard and generalized. So it's a locally ringed space such that the topological space is second countable and Hausdorff. The sheaf of the structural sheaf is a subsheaf of the continuous functions, and the space is locally isomorphic to the local model. The morphisms in this category are just morphisms as locally ringed spaces, and they are induced by continuous maps between the underlying topological space, just by composition. Okay, and just to finish this section, I want to remark that the topological space is a topological space with boundary, but moreover that the analytic structure induces in a natural way a stratification of the boundary, right? How is this a stratification? So if we take a point and we fix a chart, we can denote by EP the number of vanishing components of the image of the point. So this number does not depend on the chart. Then the map sending to each point in the boundary, the number EP is well defined, and the strata are the connected components of the fibers of these maps. Yeah, well, and just that we can extend the stratification to the whole space, because when the point does not belong to the boundary, this number is 0, and reciprocally. Well, here we have a picture of this stratification in a so a local picture. We have something of dimension 3, and the point P has the number EP is equal to 2. That means that there are two boundary components passing through the point. The point Q has just one boundary component passing through it. And for example, the red point, that is something that we call a corner, has three boundary components passing through it. So many components as the dimension of the space. Okay, so let us talk now about the statements. So the first thing I'm going to talk is about the minimal support of a function at a given point, of a generalized function at a given point. So once we fix a coordinate system, a local coordinate system, we know that the function has a power expansion, and the good property that we have asked to the support allows to give a finite presentation, that's proved by Van den Dries and Spijziger, allows to give a finite presentation of the function in the form monomials times units. Yeah, the UIs appearing in this formula are units. And moreover, this finite presentation can be taken minimal in the sense that the exponents are 2 by 2 incomparable for the division order in Rn, where this division order is written here, says that an element alpha is less or equal than beta if and only if it is so coordinate component by component. Then the minimal support of the function at the point P, of course, with respect to the fixed coordinates, is the set of that exponents. Okay. So although this minimal support depends on the coordinates, what is independent of the local coordinates chosen is the number of monomials. When I say monomials, is the number of elements in the minimal support. So this number is called the monomial complexity of the function at the point. And when this monomial complexity is 1, it's when we say that the function is of monomial type. That is, it's a monomial times a unit. So what means, or how can we interpret to be of monomial type? Okay, so we can assimilate the boundary as a normal crossings divisor, a simple number crossings divisor. And to be of monomial type, it's something like saying that the set f equal to 0 and the boundary have normal crossings at the point. Yeah. So for example, if we take the origin of R2 and the function y minus x to the lambda, and we see it inside the right semi-plane, this function is a coordinate function in this space. Then, well, this, this I prime must be an F. I tilde must be an F. So we can put this F as a function, and we see the normal crossings property. Well, it's just a picture, but. So the monomial complexity is 1. This function is of monomial type. But if we see the same function, but inside of the quadrant, the monomial complexity is 2. So we cannot put the f as a coordinate function in a way compatible with the boundary. So y is not a coordinate function because what means the square root of this f? You know, which generalized power series is so elevated to 2 gives the function f. Okay. So now I have here the statements. So first of all, well, we have a generalized function and a point in the manifold. And what is the local monomialization problem that was solved by Martín Villaverde, Roland, and San Sanchez? So it says that there is a finite family of pairs consisting, on the one hand, on composition of finite sequences of blowing ups, and on the other hand, in compact subsets of the spaces obtained after blowing up. In such a way, the union of the projection of these compact subsets gives a compact neighborhood of the point, and such that the total transform of the function f by each one of these sequences is of monomial type in all the points of the compact. What is the statement of global monomialization or reduction of singularities? So we can say that there is a neighborhood of the point and a finite sequence of blowing up, so we have to remove the word local, such that the total transform is of monomial type at each point. So that is the same that saying that in the family of the local monomialization, the number capital N is equal to 1. And of course, we remove the word local. Okay, so, but what is, so the question now is, what is a blowing up between generalized manifolds? Yeah. So we can think, we can start with the local, so we can try to give a local definition from the local point of view. And we can consider the local model. So the first quadrant with the generalized functions there. And we can act like if X and Y, that are the natural coordinates in R2, so we can act like if they are standard coordinates and perform the blowing up. And after that, we obtain a space that we can enrich, adding all the generalized power series that can be written with the coordinates in this. So with when we read the manifold in coordinates. Okay, but we can perform a generalized change of chart that we have here. Here. So V equal to Y. This Y must be V, but doesn't matter. And U equal to X to the lambda. And we do the same. We think in U and V as standard coordinates. We perform the blowing up, and after that we enrich the structure. So what we see is that there is no an isomorphism from one manifold to the other in such a way that the diagram commutes, because we should send the point here to the wall divisor, and that cannot be. So what we are saying essentially is that the blowing up depends on the coordinates. So how we can give a definition, a more intrinsic definition, and that works for not just for the local case. So we need two ingredients. On the one hand, we need something that is called an standardization of the manifold. And standardization is consists on choosing a standard substructure of the sheaf. Yeah? So in such a way, this manifold is a standard analytic manifold, but also such that when we enrich the structure, so when we add the functions that are seen in coordinates as generalized functions, we recover the original manifold. Okay, so in the local frame, say standardization is the same as saying choosing local coordinates. Okay, and the other thing that we need is the center, the geometrical center for the blowing up. So we need a subset of the topological space such that it is given in some coordinates, but for the standard manifold, it's given as zeros of these coordinates locally at each point. So we know what is the standard blowing up with center set. And there is a result given by Martín Villaverde, Roland, and San Sanchez that says that the morphisms of G manifolds need to have a local monomial type expression. Blowing ups has this local monomial type expression. Then we can talk about the enrichment of, we can see this morphism, but as a morphism between the enrichments. We can talk about the enrichment of this morphism if we want. So, and this is the blowing up with center, the pair, the geometrical center, the set, and the standardization, the standard structure. But here we have a remark that is very important, that is that when the manifold is global, global means that it needs to be covered by at least by two cards, may not exist a standardization of the space. This is like the exotical cylinder that Martín Villaverde, Roland, and San Sanchez give in their paper. And well, just a remark that in general, this remark is a consequence of the local expression of generalized morphisms, that the enrichment is not functorial between, so does not leave all the morphisms. For example, if we send xy to the to x plus y, the quadrant to the semi-line, that gives a morphism of standard manifolds, but not a morphism between generalized manifolds. Again, because we need to talk about the square root of this sum. Okay, so how can we think about the problem of global monomialization, of reduction of singularities? So the ideas will be, let us adapt the standard strategies. But we find a big obstruction, that is that maybe a reasonable strategy that we have requires us to blow up some geometrical center. But what happens if this geometrical center is not standardizable? So how we perform a blowing up modifying it? With our definition, with the definition we have of blowing up, we can't, essentially. So the first approach we take is the stratified reduction of singularities. We take a stratified version of this problem that I'm going to introduce now. So here is the statement. Again, we have a generalized function and we look at a point. And we say that there is a neighborhood of the point and a finite sequence of blowing ups such that the total transform is stratified monomial. Okay, moreover, this sequence of blowing ups can be taken combinatorial. So let us see what means to be combinatorial or what means to be stratified monomial. Combinatorial is just that the centers of blowing ups are adherents of strata of the natural stratification. Okay, we have the natural stratification induced by the analytic structure, and we just can blow up in the adherents of this strata. When the dimension of the center is 0, we say that it's a corner. When the dimension is 1, we say that it's a net. And when the dimension is n minus 1, we say that it's a component of the boundary. Then a combinatorial blowing up is a blowing up such that the geometrical center is combinatorial. Okay, and now let us see what it means to be stratified monomial. Well, we recall the finite, the minimal finite presentation that we have at the point. So, well, we take a stratum and we take a point there, and we recall that we have a minimal finite presentation of the function. So we can regroup the terms. And so in order to write it like monomial in the set coordinates, that are the set coordinates are the generalized coordinates of the function, the ones that are not standard, times something that it's not more a unit, but when we do set equal to 0, it's non-identically 0. And we can take it also minimal in the sense that these tau j's are 2 by 2 incomparable with the division order. So the minimal support of the function f along the strata is the set of these taus. Okay. Of course, also this minimal support depends on the coordinates, but not the number of monomials. So it makes sense to talk about the monomial complexity of the function along a stratum. As a remark is that if we pick a point in the stratum, the monomial complexity at this point is in general greater or equal than the monomial complexity along the strata. The stratum. Because maybe in this when I have these v's where for the y's, for the points where the y variables vanish, so the monomial complexity is higher than the monomial complexity along the strata. So we say that the function is stratified monomial if the monomial complexity along the strata is always equal to 1 for any strata.
Exactly the infinite.
Sorry?
Is it the infinite? I mean, you have this bound. So it's exactly the infinite. Or can it be strictly less than the
here. Yes, it's so a generic point of the stratum is going to have the same monomial complexity than the complexity along the stratum. Yeah. So I guess yes, it's the minimum. Yeah. Okay. So well, we have an horizontal stability property for this monomial complexity. That is, if we have two strata and one is contained in the adherents of the other, so the smallest has a bigger complexity than the big strata. Yeah. So if S prime is contained in the adherents of S bar, means that the dimension of S prime is smaller than the dimension of S. And we have that. So we have that it is enough to work with the smallest strata. Yeah. So now I want to give a sketch of the of the proof. So first of all, what we see is that we can reduce the problem to work with manifolds with corners. I mean, for example, we can reduce to work to do the proof for a corner point. Okay. For example, if we have the point that is like here, so it's not a corner, this manifold around this point can be seen as a corner times the line. So times something, product with something without boundary, with something that is indeed standard analytic. And like since the blowing ups are combinatorial, so what we see always is a combinatorial sequence of blowing ups starting on the corner and all the time product with the same standard manifold without boundary. So in this case, we have it's R3 if you want, and in dimension 3, and the blowing ups are always étale in the strata we are looking. So and moreover, if we prove, so we have now a function, we have now our function. We can, in some sense, restrict the function to the corner, and a stratified reduction of the restricted function gives rise to a stratified reduction of the original function. So in that way, we can restrict to work to start with the case where the point P is a corner point of the manifold. So that allows us to give, so what we are going to do now is introduce a combinatorial language, so to codify this geometrical problem. Okay. So we have we are going to introduce what is the category of monomial manifolds. It's going to be a subcategory of monomial, generalized or standard. The definition works for both categories. So we have a manifold. We can think in the generalized case, but doesn't matter. We have a generalized manifold, and with corners. We need to ask it to have corners, and we ask it to have a distinguished atlas that has one chart by each one of the corners so it's covered by charts in each one of the corners of the manifold. But moreover, these charts are affine, and the definition domain is the star of the point, we can say, is the union of the strata that contains the point in the other ends. But moreover, we say that this atlas is monomial if the change of coordinates have a purely monomial expression. What does it mean? Well, we put here an example. For example, if we have two corner points P and Q connected by an edge, the edge is defined by, and we assume that the edge is defined by the n-1 first coordinates in P, and also by the n-1 coordinates in Q. Then the change of coordinates should have expression like this one. Yeah. So X, the the coordinates in Q, well, the coordinates in Q that are associated to the edge must have the same, well, I have put the same index, but that's up to reorder. Must have in this coordinate in P with the same index a real positive exponent, and the AL that I put doesn't matter if it's positive or 0 or negative, doesn't matter. So in that way, we codify this change of coordinates by means of a matrix of exponents. So this matrix can be read as, so xp1, xq1 is equal to xp1 to the power of gamma 1 times xpn to the power of a1, and so on. We read it by rows. So we can associate to the monomial manifold the collection of these matrices of exponents. And this combinatorial data is essentially equivalent to have the monomial manifold. So if we have the combinatorial data, we can recover the manifold. That is. So in the same way, we define the M morphisms. Here all the time, this M means from monomial. They are morphisms between generalized manifolds, such that maps corner points into corner points and have a purely monomial expression in the distinguished atlases in each one of the manifolds. Then they also can be codified by a family of matrices of exponents. And well, a special case of morphisms, of monomial morphisms, is the combinatorial, it is the M combinatorial blowing ups. To introduce it, we need to talk about M standardizations that are standardizations joined with a monomial atlas, but that is a monomial atlas for the standard manifold. It's a monomial atlas, so the change of coordinates is a function in the intersection of the stars. Okay, and such that it is monomial with respect to the original coordinates in the atlas A. So a monomial combinatorial blowing up is it's a blowing up, but also, so given the blowing up, with a chosen monomial atlas for the manifold obtained after blowing up. Yeah, we can, so if the center is combinatorial and the standardization has a monomial atlas, we can choose a monomial atlas for the blowing up in order to have a monomial morphism. Okay, so with this, we can talk about what is a monomial star. That is a composition of a finite sequence of M combinatorial blowing ups, and the first, so it's over so here we just have a coordinate because this is something local. It's a corner, what we call an M corner. The key result that we prove by means of all the combinatorics, by means of all these exponent matrices that we have given, is the abundance of these M stars. That is, the manifold, the end of the star is an standardizable manifold, and moreover, if we fix local coordinates at a coordinate point that are codified by a wave vector, we can extend globally the standardization. So we can take an standardization with a monomial atlas in such a way these local coordinates belongs to the atlas, are the distinguished coordinates in the point. So with this result, we see that there exists, so we can blow up this space. So there exists stars of H, R+1, and so on. And what we also conclude is that if the strategy requires us to blow up, to choose a specific wave vector at some local point, so we can do it. So we are going to consider the case of two monomials. So we start with an M corner that it's something local around a corner point with a coordinate system fixed, and a generalized function that we can assume that is the sum of two monomials. Yes, if we insert units before, if we insert here units, so in the coefficients doesn't matter, the strategy is the same. And if we have more monomials, the strategy what says is that you can go taking the monomials 2 by 2, and you first choose a pair, the singularized, choose another pair, the singularized, until you finish with all the pairs. So essentially, this is the case that we need to resolve. Okay, we fix an M star, and we take the transform of our function by this star. So for any corner point and the coordinates choose in the monomial atlas, so in the monomial atlas that we obtain after with this star, we have that this straight transform is also the sum of two monomials in these coordinates. And with which exponents? Well, they are the exponents obtained by multiplying the original ones by a matrix that codifies the data of the star at the point. Okay, so now we take a codimension 2 combinatorial center that is given locally at a point by the zeros of two of the coordinates. So for example, the Y and the J coordinates. And we say that it's uncoupled for F0 if, when I take the exponents corresponding to this index Y and J, and we see the segment that joining them, the slope of this segment is negative. Okay. So we put a P in between brackets because to be uncoupled does not depend on the point. This point is on the point P, on the point P inset, of course, in the center, in the codimension 2 center. Then we have here the invariant. So before giving the invariant, just two observations. First one is that the function is a stratified monomial if and only if the monomial complexity is 1 at all the corner points. That's because of the horizontal stability established. And the other remark is that if the monomial complexity, if at a corner point is 1, it's because there are not uncoupled centers passing through the point. Then we can define as invariant the number of, this is an M, set sub M, the number of uncoupled centers of codimension 2 for the function F0. Then the invariant is 0 if and only if the function is a stratified monomial. So the goal now is to make drop this invariant. To do it, we talk about adapted monomial standardizations. So we have an uncoupled center and a monomial standardization that locally at a point of the center is seen, is defined by a wave vector. Then this standardization is adapted to F0 with respect to this center if the two entries corresponding to the indexes defining the center gives a perpendicular vector to the segment we have. Well, this is to be adapted at the point P, but what we also see is that to be adapted does not depend on the point. So if it is adapted at one point, it is adapted at all the points. Again, at all the points, again, this point is point in seat, in the center. Okay, so with the strategy. So we take an uncoupled center for F0. After that, we take any corner point in the center and local coordinates adapted to the function. We extend globally this local coordinate to a global M standardization that we know that we can do it. And we perform the monomial combinatorial blowing up associated to this center. So what we get is that the invariant of the new star, so with one blowing up more, is just one less than the invariant before, because the codimension 2 centers that I have not modified continue being uncoupled, but there are no new codimension 2 centers belonging to the exceptional divisor uncoupled for the function. So I remove one on the list. And well, just to finish, just some open questions. The first one can be to have a stratified reduction of singularities, but instead of having centers of codimension 2, with centers contained in the non-monomial locus, so in the spirit of the reduction of singularities of Hironaka. The second one may be to have a stratified reduction of singularities, but following a standard shade. Yeah, that is each time that I take standardizations, we have a standard. So we have a standard line below that follows the same, yeah, more or less. So because the standardizations that we consider here in general does not come from blowing ups. Yeah, so in this case, we need, for example, to have these standard manifolds coming from blowing ups. And of course, a third objective will be to have a global reduction of singularities, well, at least in dimension 3. And that's all. So thank you very much for the attention.
Thank you. Okay, so we have some time for questions and comments.